Hi, welcome back to AP Chemistry with Mrs. Mays. Today we're looking at spectroscopy. That is, when we get to use light to see very small things. In this podcast, we'll focus on nuclear magnetic resonance, also known as NMR. And in AP Chemistry, you have to know about the three other types of spectroscopy: PES, UV-Vis, and IR. But nuclear magnetic resonance is also very useful, and you'll get to learn more about that in organic chemistry. So I'll give you just a quick introduction today, understanding that there's lots more details about NMR that you'll get to later on in your studies. So, of course, nuclear magnetic resonance is called NMR, and it utilizes radio waves. These waves are very low frequency, that is 10 to the 4 to 10 to the 8th hertz. And because it's low frequency, that necessarily means it's lower energy levels than the other types of spectroscopy. These will have no effect on the electrons in particular, because the electrons need more energy than that to move around. It also has no impact on the position of the nucleus of an atom or of the bonds in the molecule. So if it's not moving electrons and it's not moving the nucleus, well, what the heck is it doing? Well, it's causing a change in the nuclear spin. And anytime we connect the spin and a charge together, it creates a magnetic moment. Therefore, when we apply a magnetic field, we have nuclei that are either lining up with the magnetic field or they would align against the magnetic field. So we can apply this then to detect the types of bonds that can be found in organic molecules. And that's why you'll study this in organic chemistry. The internal magnetic fields at a molecule differ at each chemically distinct site. And by chemically distinct, we mean that the presence of electrons is going to alter the electronic environment, which then subsequently alters the magnetic environment of the nuclei. And this then creates a pattern that reveals the structure of the molecule. It shows a bonding pattern. We can also use NMR to produce visual images of the human brain and other soft tissues. And when we use this, we call it getting an MRI. Some of you may have had an MRI before. So here's an example of ethanol H1 NMR. And when you see this H1, it means that we're using the frequency to target the hydrogen 1 nucleus, the type of hydrogen that has a mass of 1. And another type is called C13 NMR that targets a carbon 13 nucleus. So this is the H1 NMR for ethanol. So we want to look at a couple of different things. First of all, how many different types of hydrogens do you see in an ethanol molecule? Well, the first type that I see is this hydrogen on the end. This hydrogen is the only one that's connected to an oxygen in the alcohol group on the end of the ethanol molecule. So that hydrogen is going to have a different signature in the NMR than any of the other hydrogens. Then in the center, we have hydrogens that are connected to a carbon in a CH2 grouping. We have a different group where they're connected in a CH3 grouping. And those hydrogens will also experience a different electronic environment because the arrangement of hydrogens around those atoms vary. So there are three different types of hydrogen atoms in the ethanol regarding NMR. The hydrogen that's on the OH group is not coupling with any other hydrogen atoms. It's the only hydrogen that's there, so we get just this one peak because it's not interacting with other hydrogen atoms, it's just interacting with an oxygen atom. We call this a singlet because it's one peak. But the CH3 and the CH2 hydrogens are coupling with each other because they interact not only with the carbon atom, but also with the other hydrogen atoms, resulting in a triplet and a quartet. So this type of hydrogen is getting split by the neighboring CH3, and this hydrogen grouping is split by the neighboring CH2. The hydrogen that's attached to the oxygen isn't interacting with other hydrogens because they're too far away to have any effect. So this is the type of information we can get from an NMR spectrum, and when you get into organic chemistry, you'll learn how to read these for yourself so that you can identify molecules and tell what they are and how they're bonded together.